So as a first step, we will show that these three metrics induce equivalent topologies, and so let me define what that means. Let D and rho be two metrics on an arbitrary space X. The topologies induced by them are equivalent if their collection of open sets coincide. So given any topological space X, there may be more than one set of basis elements, and that's in general what we're saying here is that given two metrics on a given set X, the topologies induced by them are equivalent if their collection of open sets coincide. In other words, the topology is the same, but the basis elements may be somewhat different. All right. So now we'll prove a theorem. Let D and rho be metrics on an arbitrary space X if there exists a positive number k such that the distance between 2 points in the metric D is less than or equal to k times the distance between the same 2 points in the metric rho. Then the collection of open sets generated by D is a subcollection of the collection of open sets, or in other words, subcollection of the topology induced by rho. All right, so now we'll prove this. So let the set U be open in the topology generated by or induced by D. I'll just indicate it as the metric space. Then, for every point X in the set U, there exists a basis element, which is an open ball in the metric D, centered at X, with some radius epsilon, some positive radius epsilon, such that the point X is in this open ball, which is a subset of the set U. So let the point Y be in the open ball in the metric rho, centered at the point X, with radius epsilon divided by k. Then the distance in the metric rho from X to Y is less than epsilon divided by k. Now, since the distance in the metric D from X to Y is less than or equal to k times the distance in the metric rho, it is less than k times epsilon divided by k, which is epsilon. That is, the point Y is in the open ball in the metric D, centered at X with radius epsilon. So we have demonstrated that the open ball in the metric rho centered at x with radius epsilon divided by k is a subset of the open ball in the metric D, centered at x with radius epsilon, which is itself a subset of the set U. That is, for every open set U, there exists a basis element in the topology generated by the metric rho that is a subset of x and contains the point x for every point in the set U. That is, every open set U in the topology generated by the metric D is open in the topology generated by the metric rho. All right? So we will now show that the taxicab metric D sub 1, the Euclidean metric D sub 2, and the square metric D sub infinity all generate equivalent topologies. So first notice that for every index I, that the absolute value of the difference of the components x sub I and y sub I is less than or equal to the square root of the sum of the square differences and so this is certainly true for the maximum value that we obtain when we take the difference, the absolute difference between the two components. So we have that the max value x sub I minus y sub I, absolute value of x sub I minus y sub I, is less than or equal to the metric, the distance in the Euclidean metric between the points x and y. That is, the square metric, or the distance between 2 points in the square metric, is less than or equal to that distance between those same 2 points in the Euclidean metric. All right? So now, by iteration of the triangle inequality, for the Euclidean metric, we have that the distance between x and y is less than or equal to the distance between x and z1 plus the distance between z1 and z2, and so on, plus the distance between z sub n minus 2 to z sub n minus 1, plus the distance from z sub n minus 1 to y. Now this is true for any choice of the points or vectors z sub 1, 2, and so on up to n minus 1. So let z sub 1 be the point that has as its first component y sub 1 and as its other components z sub 2, z sub 3, and so on up to z sub n. Z sub 2 has as its first two components from y, and then the rest of the components are from x, and so on, so that z sub n minus 1 is y sub 1, y sub 2, y sub 3, and so on, to y sub n minus 1 to x sub n. So with this, these choices, we have that the distance in the metric, Euclidean metric between x and z sub 1 is x sub 1 minus y sub 1 quantity squared plus zeros elsewhere. That is the square root of the square of the difference between x sub 1 and y sub 1, that is the absolute value of x sub 1 minus y sub 1. And so d sub 2 from z sub 1 to z sub 2 is the absolute value of x sub 2 minus y sub 2, and so on. So d sub 2 of z sub n minus 1, z sub n minus 2 to z sub n minus 1 is x sub n minus 1 minus y sub n minus 1. And finally, d sub 2 of z sub n minus 1 to y is the absolute value of x sub n minus y sub n. So by an iteration of the triangle inequality for the Euclidean metric, we have that the distance in the Euclidean metric from x to y is less than or equal to that same distance in the taxicab metric from x to y. So now, clearly, if we take the sum from 1 to n of the difference between x sub I and y sub I, the absolute value of x sub y to y sub minus y sub I, then this is less than or equal to n times the absolute value of x sub alpha minus y sub alpha, where this is the largest of the differences. That is, it is the distance in the square metric. And so we have that d sub 1, the distance from x to y in the taxicab metric, is less than or equal to n times that distance in the square metric. So we have completed a chain. That is, the distance in the square metric between x and y is less than or equal to the distance in the Euclidean metric between x and y, which is less than or equal to the distance in the taxicab metric between x and y, which is less than or equal to n times that distance in the square metric. And so by the previous theorem, the three metrics generate equivalent topologies. Okay, so now we know that the topologies generated by these three metrics are the same. So the question is, what is that topology? And I've made the claim that it is the product topology, so I now need to prove that. The topology on finite dimensional rule space induced by Now I can choose any one of the metrics, but I'm going to choose the square metric. Is the same as the product topology on finite dimensional real space. Okay, so we'll now prove this. So let the set U be open in the product topology. Then, for every point x in the set U, there exists a basis element B, which is A sub 1, B sub 1, cross, and so on and so forth, to A sub n, B sub n. That is a finite product of open intervals, such that the point x is in this basis element, which is a subset of the set U. Now for every index I, there exists an epsilon sub I, a positive value, such that x sub I minus epsilon sub I to x sub I plus epsilon sub I, that is the open interval, is a subset of the open interval from A sub I to B sub I. So if we choose epsilon to be the smallest of these individual epsilons from E sub 1, epsilon sub 1 to epsilon sub n, then the point x is in the open ball in the square metric centered at the point x with radius epsilon, and this open ball is a subset of the basis element in the product topology, since each interval is a subset of the interval in the respective interval in the basis element, and this is itself a subset of the set U, which is open in the product topology. So in other words, for each open set in the product topology, there exists an open ball in the square metric that contains that point and is a subset of the set U. That is, the set U is open in the topology generated by the square metric. So every open set in the product topology is open in the topology generated by the square metric. So conversely, let the set U be open in the topology generated by the square metric. Then for each point x in the set U, there exists a basis element containing it, and that is an open ball in the square metric centered at x with radius epsilon, and that is a subset of the set U. Now notice that this open ball is the product of intervals, that is x sub 1 minus epsilon to x sub 1 plus epsilon, and so on up to x sub n minus epsilon to x sub n plus epsilon. That is, this open ball is itself a basis element in the product topology. And so every open set U in the topology generated by the square metric is open in the product topology. And so the two topologies are the same. That is, the square metric. The square metric induces the product topology on finite dimensional real space.